All right. So I'm going to switch over to talking about greedy output strip. Before that, a little note on some things that I didn't mention that I think it's important to mention. So we looked at various dynamic programming algorithms, and in particular, we looked at subset sum and knapsack. And we observed that the running time would work out something like n times s, where s is the size of the set that the target set you want. And for knapsack, it was n times c, where c is the capacity of your stack. And we were, fairly happy with this. We got a dynamic programming solution, and we're all good with this. Both of these problems are NP hard. Some of you may be familiar with already, but others may not be. The point is they're generally considered intractable to solve, and yet we solve them. What's the problem? There's a catch here, and the catch here relates to sort of a thing that we don't often talk about, but we should keep in mind, namely what it means for an algorithm to have an efficient running time. Now, whenever we talk about the running time of an algorithm, we say, oh, it's n to this, n to that. We don't really pay much attention to what n is. We always think, well, if you're sorting, n is a number of points. Okay, fine. But really, n is not the number of objects in your input. N is the size of the input. In other words, n is usually considered the number of amount of the length you have to write down the input. Okay, that's n. Now, in the case of objects, if you have to sort a bunch of numbers, we kind of ignored the fact that we weren't talking about what the numbers were. We just said, okay, there are n numbers. We didn't say anything about how they're written down, so there are n blobs. We didn't count the size of a blob, so it's the size of n times the size of a blob, which you pretended not to pay attention to. But if we have to pay attention to these things matter. And in particular, they matter because for something like this is not a polynomial running time in the size of the input. Let's think about why that is. So if you think about how you represent numbers, right? A number is obviously represented as binary format, right? So if you have a number, so let's say I want to represent the number, 8, and I have an integer to represent number 8. Of course, there's going to be a bunch of zeros, but I'm going to have a bunch of zeros, and I'm going to say it's 1, 0, 0, 0, right? This is a binary representation of 8. And you can choose your favorite representation. It doesn't fundamentally matter. Right? And so, if you think about the number of bits required to represent a number, let's say a number, there's some number, let's call it b. If you think of the minimum number of bits you need to write down the number v, the number of bits you might end up using in the input, the number of bits you would use is something like log v. We will put a little ceiling on this. Right? That's the number of bits you would need to write down this value. So if I give you an input value v, the length of that input is actually log v. And something you should keep in mind is that v is roughly 2 to the log v. So the actual value is exponential in the size of the input representation. Now let's go back to subset sum. Let's go back here. We said that the input, the specification for subset sum was a bunch of numbers, their sizes, and an overall size capacity we want to target. And that number was given to us as a number, which means it's the size of its representation is log s, not s. So if you think of the numbers, if you look at subset sum, so you have numbers, you have numbers 1 through n, and they all have their own sizes. And let's say, so their sizes S1 up to Sn, and there's this number S. The total length of this input is going to be log S plus sigma over I log Si. Right? Yes? And now you have to come, and this I is equal to 1 to n. And now this is the size of my input. It's not n, because I'm using n for the number of items, which makes things confusing, but this is the size of the input. But the running time of my algorithm is n times s, which if we had to express as a function of these things, you already see a problem, because now this term here is exponential in this number here. So a running time of n times s is actually exponential in the input size. So even though my dynamic program is, it seems to work and I can get an answer for subset sum, it's not actually solving subset sum in time polynomial in the input size. And that's why I haven't actually solved it in complete problem. Because I haven't actually given you a solution that's polynomial in input size. And the same thing applies in abstract as well. Now we'll return to these issues later on when we talk about intractability and incompleteness. But I just want to flag this point here in case any of you are wondering, what is the catch? These are not easy problems. And the other point I want to make is that dynamic programming is useful even if your problems are intractable. You can actually solve intractable problems a little bit easier using dynamic programming. That doesn't mean you'll get a polynomial time solution. And in the assignment, which I will hand out tonight, we will explore this a little bit more for another problem that we looked at in class. Okay, so is there any, before I move on, I just want to make this point clear so that there wasn't any confusion about what exactly I was promising you. Dynamic programming is a design technique. I'm not also promising you a guaranteed efficiency or guaranteed polynomial time algorithm. I'm guaranteeing you that you can actually solve the problem, and it's in many cases one of the better ways to solve the problem. But if the problem is intrinsically intractable, you are going to face it. Okay. All right. This is still better than, say, doing exponential search. Let's be clear, right? An exponential search over all subsets would be 2 to the n times some, linear amount of work to add up to subset C. That's much worse than this. So just because it's not polynomial time in the input size doesn't mean it's bad. Not all non-polynomials are the same. They're all different. That's a much better non-polynomial. Right? So that's what you do. Okay. All right. Are there any questions about this before I move on? Before I move away from that? Okay. And I've seen all the assignments been pretty loose, so we start grading them very shortly, and hopefully we'll have some feedback for you even before we finish the grading, just to give you a sense of what's going to happen, in terms of how we think about grading these problems. This case you can work in the next one, which is going to be on that programming, which we'll see tonight. Also a reminder that hopefully you're thinking about what you want to do for your project, and that's due this Friday. Okay, so let's talk about video algorithms. So I like to think of algorithm design techniques as drinks. So you've seen divide and conquer. It's kind of like milk. It's very basic. Everyone makes it. It's good at work as well. Dynamic programming is like a spinach smoothie. It tastes terrible, but it's really good for you. Greedy algorithms are like Coke. Everyone drinks it, but they're terrible for you. And you should try to use them, drink them as little as possible. So why am I teaching you the greedy algorithms? Because they're so fundamental, they're so natural. They're the first thing you will instinctively come up with, that you have come up with in class many times, and they're almost always not going to work correctly. But there are a couple of cases where they do work. So now, in order to understand the power of this very dangerous can of Coke, you have to understand where it works, why it works, and why it doesn't work. Its limits, its potential has limits. Okay? So a greedy algorithm, just from the name, should tell you what it is. At each step of the process, do what seems best right now. Right? If I have to get across the room to the other end there, my greedy algorithm would be to walk all the way till here. Don't worry, I'm not going to collide with you. Suddenly I get stuck, I can't go any further. I look around, okay, well, I don't know, I'll try to go this way, and I'll try to go this way. I'll try to find some way to get there. Whereas, maybe a better, faster approach is to go right this way. But greedy algorithms don't care. They're very mild. They only look at what's good right now. If you're coming down from, You're going up on a hike in the cottonwoods and you want to come down. A greedy algorithm will say, take the steepest way down. Needless to say, that's not the best idea. But if you're skiing, it may be a good idea. Take the steepest way down, if that's your inclination. So a greedy algorithm is an algorithm that always, at every step, decides to do what seems the locally best thing to do, right, in order to further its goal. In other words, it means that if you want to get somewhere, you take the path that seems to get you there most direct, right? Even if later on you're going to hit a huge obstacle, it doesn't matter. So the design strategy is very simple. The details of how it works depend a lot on what it means to be right now, what it means to be look around and do the best thing, and all kinds of things like that. And I will say one thing just to sort of whet your interest is one of the most, probably the most popular algorithm design technique that's in use right now in deep learning. It's called stochastic gradient descent as a method for doing for finding the parameters of a neural network. Gradient descent is a greedy algorithm. Stochastic descent is gradient descent where you have a coin in your pocket and you toss them there. So greedy algorithms are everywhere. They are very heavily used. They work very well in certain situations. They work terribly in other situations. And one of the jobs in algorithms class is to tease out when they work. Okay? All right. And so let's, as always, start with an example so we can get a feel for how a greedy strategy might look and how we might reason about why it works correctly. Okay? Okay, so this is the problem. I have a bunch of jobs. Each job has a duration. Okay? And I want to schedule them back to back. So think of these as programs running on a single processor machine, let's say. And each job is owned by someone else. And people will be very unhappy if their job takes a long time to finish. Or if the time at which their job is finished is very far in the future. So what you want to do is make sure the average completion time of a job is minimized. So on average, you try to balance out everyone's needs, which basically means, if there are, so let's say we have an example here. So let's say I have 4 jobs. The number inside is the duration of the job. And if I schedule them in this order, exactly this order, the first job would complete at time 3. So that's 3. The second job would complete at time 4. So 3, 4, 6, 12, right? So then 12 plus 6 is 18, 18 plus 4 is 22, plus 3 is 25. So the average completion time is equal to 25 divided by 4, which is equal to 6.2. My goal is to minimize this number. So for example, what I could do, let me see if I can do this easily here. So what I could do is move this out, slide this up this way, and move this one here. Okay? Now let's see what it looks like. So now we have 1, 4, 6, 12. Right? So 12 plus 6 is 18. 18 plus 4 is 22, plus 1 is 23. So now we have the average completion time is 23 divided by 4, which is equal to 5.75. We made progress. So now you have n jobs. Of course, you can imagine any possible order. A brute force strategy might say, enumerate all possible orders. That would be terrible. Or take n factorial time. We don't want that. You could try to design a divide and conquer strategy. You'd probably want to split the items in 2 groups, solve the problem recursively each part, and then someone try to merge them together. I'll leave that as an exercise for you to ponder about how that would work. You could imagine a dynamic programming strategy. You might say, well, I might say, I'm not quite sure how I would design it, but I could say, let me guess at the first, you start with the green item, and then recurs on what's left, and and then see if you can come up with a bottom-up unrolling. It's not clear to me you would be able to, but that's something, that's the way you would approach it. There are different strategies you could opt for this. But what would a greedy strategy for this problem? So a greedy strategy would say, at every step I want to do what's the best thing possible right now. So initially I've scheduled nothing at all, right? And so I want to schedule the first. If I want to be really greedy about this and I have only one thing to schedule, what would I pick to make sure the average completion time is the smallest possible? You pick the smallest one first, right? So you pick the smallest one first. So in our greedy version of the strategy, what you might do, sorry? So the greedy version of the strategy, we might say, okay, let's put the smallest one first. Okay, we've done that. It's over. Now we're here. We've got to pick the next one. What should we do? The next smallest one. Okay, so we'll take 2. Put it here. And now we have 3, and that's the next smallest, and 6. So according to our greedy algorithm, we're done. So now let's see how long this will take. This will take 1, 3, 6, 12. 12 plus 6 is 18. 18 plus 3 is 21, 22. And so this is going to be 22 divided by 4, which is equal to 5.5. Oh, good, we made progress. And now the question is, how do we know that this is going to work? So our greedy algorithm, let's write down our greedy algorithm at this point. Our greedy algorithm says, pick the and schedule. Next. And what's greedy about this is this. We're basically saying, look, if we only have one thing, that's what we want to do. So that's what we're going to do. We're not worried about all the other items. There's too much work. We don't want to think about it. We'll look very narrowly. Okay? So this is, as you can see, greedy algorithms are attractive precisely because they're very simple to state. You know, you can write down the code for this. It's not hard. But you can see exactly what you can do. And it seems to work well. And this is also the diabol. This is like, you know, this is the coke aspect of greedy algorithms. It looks fine, you know. It's all good. It looks great. But we have to know if it actually is going to work. Will it work well for any possibility? How do you know that it works? For divide and conquer algorithms, there's a standard pattern to show how it is correct by induction and how it runs by the Moss theorem. For dynamic programming algorithms, there's a standard way to tell if it's correct by induction and how to what its running time is by analysis of the table. For greedy algorithms, the running time analysis is not terribly hard. Just sort them all, sort them, do it. The correctness analysis is a kind of induction, but it's much trickier. And so the proving that a greedy algorithm is actually correct is where all the work is going to be. All your work is going to be centered on that aspect. Usually getting the runtime bound is not going to be too hard. Okay? So how do we reason about a greedy algorithm? And the way to reason about its correctness is to do something we haven't done a lot of in the past. We have to talk about what the optimal solution might be. So we did a little bit of this with dynamic programming, but not too much. But here we have to imagine this optimal solution that we don't know what it looks like. And we have to imagine what it might look like. And we have to imagine conditions under which it's not the solution of the greedy algorithm. And see if somehow we can reconcile this now. In other words, we are generally going to show the following. We're not going to show that the greedy solution is optimal. That would be nice. But we're going to show that an optimal solution could be greedy. In other words, we're going to take an optimal solution, some imagined optimal solution that isn't greedy, and we're going to keep tweaking it till it becomes the solution the greedy algorithm would give us without making its cost any worse. And I say worse, it could be either increasing or decreasing. So in other words, we're not arguing that the greedy solution is the optimal solution. That's hard to do because often you have multiple optimal solutions. We're just saying one of those optimal solutions is also going to be greedy, and then we're done. So what does that mean here? So if you remember, the greedy algorithm says, pick the item with the least duration and schedule it the next. Which is another way of saying this is that in a greedy solution, items are in sorted order of duration, increasing. Right? Because we're only the item that has the least duration of what's left and putting it, we're just sorting. If an optimal solution is not in fact the greedy solution, while we don't know what that optimal solution is, what can we be sure to say about it if it's not the greedy solution? So in other words, again, if I have a solution that is the correct answer to the problem, but it is not what the greedy solution was, what thing can we be sure to say that must be true about that optimal solution without knowing what it is? Yes, because it's optimal. What else can we say about it? Something more structural. Because it's not the greedy solution. It doesn't sort the items. So what does that mean in specific? If it's not sorted, what should we be able to find if it's not sorted? We should be able to find two items in the optimal schedule that are not in order of duration, right? Because it's not sorted. Okay. Let me make a further claim. Although I don't think it even matters. But you can say even more. You can find two items that are not sorted that are right next to each other. Let you think about that for a second. Because if you have, suppose you imagine you have two items, you have a list, and your two items are not, so this is the big item and this is a small item, and everything else is sorted, right? If everything else is sorted, everything here should be less than this one, right? That means if you keep going, there has to be an element here that's less than this. So this takes a bit more work to argue. I just gave you a sketch, it's not a proof. But without those, generally you can assume that if there are two items, if a list is not sorted, there must be two items adjacent to each other that are not sorted. It actually won't matter for this proof, it just makes it easier to draw it. So in an optimal, so we know that if opt is less than, strictly less than greedy, it must be the case that opt is not sorted, because the greedy solution was sorted. Right? Therefore, there must exist items I and j such that the duration of I is less than the duration of j, right? And what? In optimal schedule, which comes first? Sorry?
The longer one comes.
J comes before I. Okay, so remember, we have no idea what the optimal solution looks like, but we can be sure it must have this property, right? This is where we do this kind of weird imaginary reasoning about this imagined optimal solution. So let's draw a picture. Let's see what this looks like. So we have one item that's long and appears first, and we'll call this J. And we have one item that's short and appears afterwards, and we call this I. Right? Is that the picture we have right now in our optimal solution? Do we agree with that? Is there a question?
No,
Oh, this? Okay. So do we agree that this is what the picture of the optimal solution must look like? And of course, there's stuff in the middle. There's other things in between. Again, if we wanted to, we could assume they're adjacent, but it doesn't, actually in this case it doesn't matter. Okay? Alright. So what is the actually it would matter, but okay. It'll make it even, never mind. Let's say let's say that there are, I don't know, there are k items in between. J enough. K could be 0, they could be adjacent or could be somewhere. We don't, the k won't matter, you'll just see why. But there's some k. If you look at the cost of the optimal solution, adding it up just up to I, because after that it doesn't really matter, what does it look like, right? So let's say there's some total duration you paid for so far up to here. So let's call this total duration C. I'm just randomly throwing out letters. I just need something to represent this. Okay, so this is C. This is C plus J, C plus DJ. Right? Now these items in total have some duration, I don't know, any another letter. Let's call it M for middle. Okay? They have a total duration there. So this point will be C plus DJ plus M. And then this will finally be right here, will be C plus DJ plus M plus DI. Right? Okay. But these are just the markers of the completion time. So you have to look at the cost now. What is the cost going to be? Well, it's whatever cost you paid before. So you're going to pay C plus DJ, right? Plus a whole bunch of things. So it's going to be, you know, C plus DJ plus some duration, plus C plus DJ plus some other duration, plus some other duration, and so on, right? And there's going to be K of these things, right? Plus C plus DJ plus M plus DI, right? Plus a bunch of other stuff, which I don't care about. Okay? Yes?
Are we assuming the other numbers to be sorted? Or
We're not assuming anything. We just don't care. Yeah, exactly. We're just saying, okay, look, because it's not sorted, there's at least some pair that's not sorted. Let's look at that. If there are more pairs, we'll see what happens next.
Okay.
But let's just watch what happens now. Okay? So we have this here now, right? And again, this is why this is why it would have been easier to assume K is 0, but let's just, it doesn't really matter. So this can be rewritten as, let's see, C plus DJ plus K times C plus DJ plus a bunch of other things. Let's call this whole expression here I don't know, any more letters? Okay, let's call it E. Doesn't really matter. So plus E plus C plus DJ plus M plus DI plus, let's call this F. Do I have an F for it? Okay. All right. And we can simplify this. This will be basically C plus K plus 2 times C plus DJ plus E plus F plus N plus DI. Okay? All right. What would happen now if I swapped items I and J? Yeah, you have a question already? Yeah, okay.
E and K or like E cross E already has M, right?
No, because E is the yeah, sorry. Someone will think it. No, it's all good. Yeah. I'm being very sloppy here because first of all I can, and secondly it's not incorrect. Those numbers don't really matter. I just wanted to look over. If you now swap I and j in this optimal solution, what is going to happen? You're going to get the same expression, but with I and j swapped, right? You're going to do a whole bunch of additions with respect to I, and then you're going to have one with their respect to j, right? If you take the difference of these two, so this is the cost with j and I the way they are. So let's imagine that you now swap I and j and take the difference. Let's see, we know that it's optimal, so any swap should increase the cost. So let's say mu minus O. Okay. So if you take the difference of mu minus O, all the constant terms are going to go away, which is why it didn't matter. And what you're going to be left with is going to be, let's see, k plus 2 times, what did I do? Di. Check my math, see if I get this right. Minus dj, is that right? Yeah. Plus di minus dj. So this gives us, so there's one term for this, and there's one term for that, and everything else goes in. What do we know about di and dj? dj is greater than di. Is this number negative or positive?
dj minus ds because we are in mu.
Yes, that's what I thought. There was something wrong here. Thank you. So since it's subtracted out, this is basically k plus 1 times di minus dj. Right? Remember, k is 0 or more. This number is negative because di is less than dj, right? Which means nu minus old is negative, which means nu is less than old. How can that be? We just said that optimal is optimal, that is the best answer. And somehow by swapping two things, I managed to make it better. That is not possible. If it was optimal, and it claimed to be optimal, then I could not have made things any better. So there are two ways to look at this. One way to look at that is that, well, okay, let's just keep it this way for now. What this is saying is that if there is any instance of two things that are incorrectly sorted in an optimal solution, I could swap them and get a better answer, so that solution cannot be optimal. The only condition under which my optimal solution is in fact optimal is if there were no such pair on which I could do this. But if there is no such pair on which I could do this, it must be sorted. And if it's sorted, then it's the same solution as what the greedy algorithm gave me, and therefore the greedy algorithm is optimal. So you see how convoluted this argument is, right? I'm not arguing directly for the greedy algorithm saying, hey, this works, it's great, it's awesome. It's like, no. I don't care what your algorithm is doing. Let's go look at our friend, the optimal solution, and let's see what it cannot do. Okay. You will find as we go more and more in this class that often the reasoning about an algorithm is not about the algorithm, but it's about the optimal solution, and try to match it to your algorithm. And this is your first example. So greedy algorithm proofs are tricky that way. You have to reason not about the algorithm directly, but indirectly. That if it wasn't like this, bad things would happen. Therefore, it must be like this. And these kinds of proofs by contradiction are often a little hard to get your head around sometimes. The intuition is not quite as convenient as it is in other cases. Okay. Yes?
So if we had said something like averages are smaller with smaller numbers, so a sorted list will always be better. Would that's not.
So wait. You said averages are smaller, which is a sentence I don't understand.
I'm going back to the algorithm.
Okay.
So I'm just thinking like this wouldn't be the appropriate proof, right? Just to say like in order to get a smaller average, you need smaller numbers, therefore sorting the list would always give.
But I want to point out one thing. You said in order to get a smaller average, I need smaller numbers. That is correct. But remember that I'm adding up all the numbers. I'm not throwing out the numbers. I'm using them all. It's just that I'm summing up partials, some of them done in different ways. So while your intuition, okay, in order to get smaller average, I need smaller is a good intuition, it's not a proof of anything. Because what does it have to do with the algorithm? The numbers that you're referring to are all these cumulative sums. Then you have to argue that by sorting, I always get better cumulative sums. That requires a proof.
Okay. So this is like the proof you've shown us is like a general proof that will help us understand how to prove all the other types of.
For greedy algorithms. Yeah, that's right. Yeah, right. And that's the thing with greedy algorithms. It's very, very tempting to look at them and say, well, yeah, what else could you do? That you have to do this. And that intuition is a good intuition, but it's almost never a proof, and it's often easy to get sort of distracted by it and get into a wrong proof. Often greedy algorithms will not work, but they look like they'll work because of that argument. And we'll see some examples. Okay. So greedy algorithms come with a big caution label. They're useful, but you have to be very careful. It's very easy to break. Yeah.
Is it possible
okay, good. In this case, what do you think would be a condition under which the optimal solution would be? Right?
increasing order of
Wait. So
basically sorted.
you're throwing words at me, and all the words individually make sense, but you don't answer my question. What is the condition? You have the answer to your question right now because we know what an optimal solution looks like. What is the condition under which an optimal solution do you need?
Items are sorted order.
That's the solution to the optimal.
No repeating.
Why?
Because if there are repeating elements, you can swap the jobs.
No, yeah. That's the answer. The answer is not, yeah, that's what I said. You didn't say that. The answer is because, okay, let's see this more clearly. Under what conditions is the optimal solution unique? Well, we know the solution is a sorted list. When is a sorted list unique? Well, then there are no repeats. And the point is that when you're applying a greedy reasoning, you will often have solutions that are not unique. You have multiple possible optimal solutions. Which is why, think of it this way. Okay. Let me draw a picture. Okay. Let's look at this. This is the space of all possible solutions to your problem. Okay? All solutions. Good, bad, ugly, whatever. This is the space of optimal solutions to your problem. There are more than one of them in general. They might even look different from each other. In this example, it's because of duplicates, but in other cases, they may be different. They may be just different looking solutions that all have to have the same cost. Okay, all the solutions have the same cost. So these are all optimal. What I'm saying is that the greedy solution I pick, which will be a single solution, the proof I'm going to make is that it's going to be one of these things. Which is why you don't want to argue directly that a greedy solution is optimal because you might be trying to target the wrong optimal solution and it won't be that one. But it's in the set of optimal solutions. Okay? And that's what we're trying to prove here. And that's what we've shown. There are all these different optimal solutions, but the greedy solution has to be one. Okay? Alright. So let's continue on. Let's take another problem. So this problem is called interval scheduling. So scheduling is a theme that occurs often in these cases. And in this case, you're given a collection of intervals. That meaning you're given a start time and a finish time. So, Your class starts at 10:45 and ends at 11:35, right? That's slightly wrong. So starts this time, ends this time. And so think of this thing. I have just, I have a bunch of classes to schedule, and the goal is to pick as many intervals as possible. So maximize the set of intervals you pick, so that no two intersect. So you can think of it as saying you want to attend a whole bunch of classes on a day, but you can't be in two places at one time. So you can this. Or you can imagine that you have some kind of shared resource. In this case, resource your time, but maybe it's a microscope, right? And everyone has to do an experiment at a certain time, and they have to use a microscope because their flies are hatching at a certain time, and you need to use it. And you want to, make sure as many people get to use a microscope on any given day. So you have to make sure you don't have to people trying to use microscopes. So there are many different problems in scheduling that boil down to this kind of question: how do you maximally schedule intervals that don't intersect? So is the question clear? So this is kind of an interesting problem because there are many ways you can think about doing this grading, and most of them won't work. So, all right, let's see. Give you a minute or two. If you haven't seen this problem before, you're not always familiar with the correct solution. Think about what might be considered. So think about being greedy in the sense of just, aggressively trying to find something that works without thinking too hard about it. Yeah, I'll give you a minute or two, and then let's come up with some ideas for this. Let's take a minute to think. Again, let me make sure the problem is clear to all of you. If you have any questions about this problem statement, let me know. Okay. Okay. Any candidates for a greedy strategy for solving this problem? You can just shout them out, I'll write them all down. We can look them all together. Yeah.
One can be starting with a job that starts very first.
So your greedy strategy is pick the job that starts the soonest. Okay. Can you explain that? What's that intuition for you? Why do you think that would be a good idea?
Starting first, maybe I can finish one early.
Finish early because you start early. So then you can get more stuff in.
Yeah.
Good. So one strategy is pick the job that starts earliest. Okay. Any others? Any other candidates for this is a perfectly awesome greedy strategy. So just saying do something hopefully that makes sense. Yeah.
Sort them by duration and then pick the shortest one, and if it fits the schedule.
Tell me your intuition for
that. So if you choose.
So I assume you sort them in increasing order of duration?
Yeah.
Okay, so tell me your intuition for why you think that's a good idea.
Hopefully you'll get a lot of little duration, you can add as many as possible.
Good. So you want to pack a bunch of them in. If you sort them and pick them that way, you might as well pack them all in, as long as they don't conflict.
Yeah.
Good. So sort by increasing duration. Good. Anyone else?
Yeah. The end early.
What's your intuition for that one?
because we will have more if something and so basically we want the number of jobs to be maximum.
Yeah.
If something and early we have more space, more time left so that we can put other jobs.
Okay. All right. So pick job that ends earliest. Okay. Any others? Any other candidates? Okay. Developing an greedy algorithm that actually works is a sort of an iterative process of attack and withdrawal, attack and sort of withdrawal. You come up with an idea and you want to attack it as much as you can, imagining you're me and I'm trying to break your algorithm, or imagining yourself and trying to break your algorithm. If you fail to break it, then you might say, okay, this survived my first wave of attack. Let me try to prove something. Then you fail to prove something. It's okay. I failed to prove it. Let me try another more sophisticated line of attack to break it. And you often go back and forth. Hopefully you converge on something. You get a counterexample or you get a proof. But sometimes it takes a while. So let's start with an attack, because greedy algorithms are easily stated, so it's easy to attack them. Let's attack the first one. The idea is to pick the job that starts earliest, so we sort them by starting time and then put them in order, assuming they don't conflict as people not right. Try to break it. Oh my god. That was quick. Yeah, nice.
So let's say you pick a first job that starts first,
Yeah.
and if it runs for a much longer time, and there are other smaller jobs that you can put in that time, then we are not doing a job.
So a counterexample to strategy 1. That was the. It looks something like this.
Yeah.
We picked the job that started first, but it blocked a whole bunch of other ones from getting picked. So that greedy strategy was very short-sighted. You didn't realize, oh, if I just looked before the early cycle jobs, and it failed. Okay, so the other thing you must be is very, very cold-hearted and ruthless. You cannot afford to have feelings for your ideas. It's gone with no mercy. Okay, next one. Let us break the next one. Sort by increasing duration. But no one wants to break it. There's so many hands. You're going to break your own? That's great. Even better.
So if you use like classes as an example, say there's a bunch of classes that are 20 minutes long from like 9:50 to 10:10. But then there's a bunch of half-hour classes that go from like 9 to 9:30, 9:30 to 10.
Mm-hmm.
So if you choose the shortest, then you only get one every hour block.
So it sounds like what you're saying is something that, if I understand correctly, your picture is going to look like this.
The first row could be that red row that's already up there.
Pardon
Like,
Yeah.
me? But this is good, right? You pick short duration classes. They're all. This is not a counterexample for the strategy.
No, but his.
You could fit like 2 in within the space
You mean in space of one of these?
Like if they.
in between.
Like a bit here.
Yeah.
Yeah, I think I was going to. Let me draw a separate one. I think I'm trying to get at what you're both saying. I think what I'm going to draw something like this. So this is my single class, which is very short, which I picked, but there were. Is that kind of what you had in mind?
Yeah.
As an example, where you would pick the small one, but you should have picked the 2 other ones. Okay, so again, this is even more merciless because you just killed it yourself. So, boom, gone. Okay, who wants to break number 3? You've got 4 minutes to break. Okay. It's not red, it's black. Could be a hope. Right, I'll hold it before we break. Okay, pick the job that ends the earliest. Who wants to break it?
It's similar to the second case where the start time is.
So can you sort of give me a rough idea? Help me draw it.
Start time is just before the end time.
The start time is just before the end time. So there are 2 jobs, and they're right next to each other?
The start time of it is before the end time. So just was in the second case, it's starting in the beginning.
So there's one job, I'm going to start drawing them first. I'm going to look like. And there's one that comes here?
Yeah.
Okay. What's the problem now?
What if, like, if there were two jobs in the second row,
Yeah.
and he picked the first one, and then he could not choose the other two, which would fit in at the same place.
So it would be like this, you know?
Like maybe 1 minute difference or something.
Like this?
No, we had one class that ended at 11:10.
Yeah.
And then we had two classes. One
Okay,
that
hold on.
started.
Okay. Okay, one class ends at 11:10.
Yeah.
Okay.
And then there are two classes which start at 11 and 11:30. Sorry, you can see the things.
Are you retracting your counter example? Can you
Yeah.
just break your brain? Okay, yes.
So in the previous case, if the second block was longer than the first block, that would be not
So
also
give me an example. Draw an example. So this class ends at 11:10. This is
Let's
fine.
consider the window of 0 to 10, the
Yeah.
interval.
Okay, hold on. Okay, yeah.
And the first task is 0 to 3,
0 to 3,
and the second is 2 to 10.
2 to 10. Okay, what's the problem?
So the third one, so we pick the first task, right?
Yeah.
And we cannot go to the second task, but it's
Correct. But what is the correct answer?
So the correct answer is you should go to 10.
So how many jobs did I successfully schedule in the correct answer? One, right? How many jobs are correct scheduled?
The number of, but the interval,
Remember, okay, the goal is to maximize the number of jobs you pick.
okay.
Yes.
So I guess going off of this picture, so the class ends at 3.
Okay, so you have a new example?
Yeah.
Let me draw a new one here. So the class ends at 3.
Yeah, and then the next available class is from 3 to 10.
3. So let's assume that kind of not. Okay, so you want to go 3 to 10? Is that
Yeah. So the next, or I guess 3 to 10. What are like the next?
Okay, so right there to 10.
Yeah, but there are 2 smaller classes that fit, at 3 to 10 or that
Well,
go
tell me
3
the
to
starting point.
3 to 4. No. 250 to 5.
250 to 5.
Yeah.
Okay. Yeah.
And then 5 to 10. Or yeah, so you can only get.
So what's the question here? So you're saying that the algorithm will choose the purple solution, and you
Yeah.
want to choose a red solution.
Yeah, red and black. Or
There's no
red.
black.
Well, I guess there'll be another class from 0 to the beginning of the first one. So there's a total of 3 classes opposed to.
So you want from 0 to 3. Here, this one?
Yeah, so there's a total of 3 classes.
Okay, but then remember the algorithm said pick the class that ends the earliest. I wouldn't have picked that purple class then.
But if
And if you remove that, then there's still 2 and 2. You still haven't come up with a good counterexample. See, Vivek said like, I don't want to beat this yet. You should be trying to beat this to school. Yeah.
if the second purple class ends at 9:50,
The second purple class ends at 9:50. Okay, let's do that. This one, right?
yeah.
Okay.
So we'll pick that one instead
Wait.
of.
Okay.
So we'll pick that one instead of the 2 classes, like the 3 classes.
Well, no, because I would have started off picking the first red class because I said pick the one that ends the earliest.
Oh.
But then after the first red class, you pick up the.
Which is the class that ends the earliest next. I would pick this one.
Okay.
Yeah.
And then I pick this one. So we're out of time for today, but this is great. This is exactly how I want you to be thinking about your greedy algorithms in design. This is very good. I'm very glad that we're doing this process right here. But so far we have our first wave of attack has failed. So when the first wave of attack fails, the challenge, okay, maybe it's actually right. Let's think about that for next time. That's fine. I'm happy to sort of deny all possibly being right. You can live. So, but we'll talk about this next class.